The Piezoelectric Micromachined Ultrasound Transducer, or PMUT, is a really attractive device. It's essentially an ultrasonic sensor in a tiny package. In this tutorial, we're going to use a 2D axisymmetric approach to find the frequency response of the PMUT and then calculate the acoustic pressure generated at resonance. Let's get started. Open Model Wizard, select 2D axisymmetric for rotational symmetry. In the Select Physics dialog, expand Structural Mechanics, then open Electromagnetic Structure Interaction. Select Piezoelectricity Solid. This bundles solid mechanics and electrostatics with the piezoelectric coupling already wired in. Click Add. Now expand the Acoustics branch and select Pressure Acoustics, Frequency Domain. Click Add. The added interfaces list should now show solid mechanics, electrostatics, pressure acoustics, and the piezoelectricity multiphysics coupling. Move to the Study tab, select Frequency Domain under General Studies, and click Done. COMSOL builds the model tree with all three physics interfaces and the coupled study step ready to configure. Select Geometry 1 in Model Builder. Open Settings, change Length Unit to Geometry Dimensions now interpret as micrometers. Under Global Definitions, open Parameters 1. Add the parameter silicon D with expression 800 micrometers. This is the silicon membrane diameter. Enter silicon diameter as the description. Add silicon T with expression 5 micrometers for the silicon membrane thickness. The value column confirms 5e6 meters. Add star electrode T with expression 100 nanometers, which resolves to 1e7 meter. This defines the electrode layer thickness at 100 nanometers. Add electrode D with expression silicon D17. COMSOL evaluates this to 5.6 E4 min, setting the electrode diameter to 70% of the membrane diameter. Add piezo T with expression 1 micrometer for the piezoelectric layer thickness of 1 micrometer. Add the final parameter, T with expression electrode D. The piezoelectric layer diameter matches the electrode diameter. All 6 geometric parameters are now defined. Right-click Geometry 1 and add a rectangle. Label it Silicon Membrane. Set width to silicon D2 and height to silicon T with the base position at corner R0 is equal 0. In axisymmetric geometry, width runs along the radial axis. Add a second rectangle and label it Bottom Electrode. Set width to electrode D2, height to electrode T, and position the Z-coordinate to silicon T so the electrode sits directly on top of the membrane. Add a third rectangle and label it Piezoelectric Layer. Width is Piezo D2, height is Piezo T, and the Z position is silicon T plus electrode T, stacking it above the bottom electrode. Add the fourth rectangle and label it Top Electrode. Width is electrode D/2, height is electrode TT, and Z is silicon T plus electrode T. This places the top electrode above the piezoelectric layer. Add a circle to define the acoustic fluid domain. Set the radius to 500 micrometer, sector angle to 90 degrees, and center position Z to silicon T. The quarter circle represents the axisymmetric hemispherical radiation space above the device. Build all. Form union assembles 5 solids into stacked PMUT cross-section. Open the Materials node and click Add Material from Library. Search for silicon polycrystalline silicon and add it. It defaults to all domains. We'll override specific layers with the correct materials next. Add Schrost molybdenum from the library. Assign it to domains 2 and 4, the bottom and top electrode layers. Add aluminum nitride as mat 3 and assign it manually to domain 3, the piezoelectric layer. This is the active piezoelectric material for this PMUT design. Add air material, assigned to domain 5. Select the solid mechanics node. Include only domains 1 through 4, the structural layers. Domain 5, the air region, should not participate in solid mechanics. Open Piezoelectric Material 1 under Solid Mechanics. Set the domain selection to Manual and select 3 only. The aluminum nitride layer is the sole piezoelectric domain. From the Solid Mechanics toolbar, add a fixed constraint. Set boundary selection to Manual and select boundary 15, the outer circumference of the silicon membrane. Select Electrostatics node. Set domain selection to Manual, domains 1-4, air domain excluded. Open Charge Conservation, Piezoelectric 1 under Electrostatics. Assigned to domain 3. Handles coupled dielectric behavior of piezoelectric aluminum nitride. From the Electrostatics menu, add a terminal. Set boundary selection to Manual and pick boundary 8, the top surface of the top electrode. Set terminal type to voltage with 1 volt. Ground bottom electrode boundary 6. Select the Pressure Acoustics Frequency Domain node and set the domain selection to Manual, choosing domain 5 only. This confines acoustic wave propagation to the hemispherical air region. Add spherical wave radiation boundary. Select boundary 17, set Z's to 0 mm. Right-click the Multiphysics node and add an Acoustic-Structure boundary coupling, and include boundaries 10 through 14, the top surface of the membrane stack where acoustic and structural domains meet. Select Mesh 1 and add a mapped mesh operation. Set domain selection to Manual and choose domains 2, 3, and 4. The thin electrode and piezoelectric layers require structured quadrilateral elements to resolve their small thicknesses accurately. Add distribution under Mapped 1. Select boundary 10, set fixed number of elements to 50. Add a second distribution. Select boundaries 11, 13, and 14, the through thickness edges of the electrode and piezoelectric layers, and set the element count to 3. 3 elements through such thin layers is sufficient for this frequency range. Add a free triangular mesh operation with domain selection set to remaining. Set the element size to predefined fine under general physics calibration. Build the mesh. The quarter circle acoustic domain fills with triangular elements automatically. Open Step 1, Frequency Domain, and click the Range button next to the frequency field. Set Start to 20 E3 Hz, Step to 500 Hz, and Stop to 2 E5 Hz. This sweeps from 20 kHz to 200 kHz in 500 Hz steps, covering the expected PMUT resonance band. After the first compute, an error flags missing relative permittivity for molybdenum. Open Mat 2, molybdenum, and add relative permittivity of 1E10 in material contents. This satisfies electrostatics requirements for metal electrode domains. Click Compute on Study 1. COMSOL runs coupled solid mechanics, electrostatics, pressure acoustics, frequency sweep. Open the stress result plots. The 2D plot shows von Mises stress peaking near the clamped outer edge of the membrane, and the 3D revolution view confirms the axisymmetric stress distribution across the full circular diaphragm. Under Results, add a 1D plot group and label it Frequency Response. Add a point graph inside it, setting the dataset to Study 1 Solution 1. Label this point graph Amplitude. Set selection to Manual, choose 0.5 at the membrane center, and set the y-axis expression to W with YEM, the axial displacement component at the center point. Add a second point graph and label it Phase. Set the same manual selection point 0.54 and set the y-axis expression to solid.phase Z, the phase angle of the Z displacement in radians. In the plot group settings for frequency response, enable 2 y-axes and check the phase box to assign it to the secondary axis. The resulting graph shows a sharp resonance near 135 to 140 kHz with the characteristic 180-degree phase shift, confirming the PMUT first resonant mode. Open the acoustic pressure 3D result node. Set dataset to revolution 2D1, select 136E5 Hz at resonance. The 3D hemisphere shows acoustic pressure radiating from the membrane. Peak values ±80 PA confirm efficient emission. Thank you for watching. See you next time.